Today what we're going to do is just cover the notes on magnetism once again. So let's just get started. So magnets, a couple of properties of them. Magnets have north and south poles. A rule about magnets we're going to talk about a little bit later in class today is there has to be, for every north pole, there has to be a south pole. You can't just have a north pole by itself. Now, there are materials which are called lodestones or are naturally magnetic. Iron, nickel, and cobalt are the three materials that can be naturally magnetic and are easily magnetized. Just like with electric fields, magnets create magnetic fields. So the presence of a north and a south pole creates a magnetic field, and the interaction of magnetic fields creates magnetic forces. Just so kind of like how if we have two positive charges, they create electric fields and they repel. You have magnets which create magnetic fields and they also can attract repel. So as an example, I'm going to try to draw this really quickly. Maybe. Here we are. So as an example, if I have two positive charges, so this is electricity, we learned that positive charges create electric fields. And so when we have two positive charges near each other, those electric fields repel. So this tells us that the presence of electric fields creates electric forces, which causes them to get pushed apart or separated. So now, when we examine magnetic fields, if I have, for example, a bar magnet, which has a north and a south pole, the rules for magnetic fields are very similar to electric fields. So for electric fields, they always go from positive to negative. For magnetic fields outside of the magnet, they go from north to south. And magnetic fields curl from north to south. So for example, for a bar magnet, that's the magnetic field of a bar magnet. A quick note about these field lines to remind you, where the field lines are the most closely packed together, that indicates where the magnetic force is the strongest. Now, I didn't draw these lines very well because technically these lines aren't supposed to cross. So this wasn't great, but at least it gives you the rough idea. So now let's examine what magnetic attraction and magnetic repulsion might look like. So for example, if I had two magnets, so a north pole and another north pole. Now, of course, I'm not drawing the south poles, but we know that somewhere over here there has to be one. Well, when we have these two magnetic fields, we're going to see that both of these fields are going to push on each other, repel. And just like how we drew for electric fields here, you see we get the exact same picture here for two magnetic fields. And so the presence of two north poles will cause repulsion. Or if I had, for example, two south poles, we'd see the exact same effect, with just arrows going inwards. Finally, if I had a north pole facing a south pole, so two separate magnets where I could have that happening. So a north pole and a south pole like so. Everyone see that? Sorry, I just want to make sure. Then we would have the magnetic field going towards it. So notice that that picture is very, very similar to the field diagram that we showed for a positive and a negative charge. So quick reminder, for a positive and a negative charge, the field lines look something along the lines of this. So we noticed that there is a really important correlation that magnetic fields, if we look at these field lines and electric fields, they seem really related to one another. That's going to be really important for the second half, or for a few minutes later in today's lecture, because magnetic fields and electric fields really are related to one another. All right, this is a good point. Are there any questions that you'd like to ask before we continue? Or I should say, what questions do we have at this point in time? A quick note, the things, ooh, this light's not great, is it? Can you maybe thumbs up, thumbs down, sideways? Are you able to see those pictures well, or is it really glary? Cody.
It's glary but manageable.
Okay, let me try and. Yeah, okay, I guess we're just going to make do. I'll try to change where I do the lessons for next time. Okay, so we're going to go ahead then. Does anyone have any questions? No, okay. I heard my little dinger going off, so it sounded like more people were entering the class. If you came into the class a little late, just make sure you go to the chat and put your name in so I can record attendance. Okay. So, scrolling back down. Now that we're kind of back on the same page, we've talked about magnets. Let's talk about some applications of magnets, where they're used. The first one is in the storage of information. So when I finish this lecture and I save the recording of the chat, or when I'm making these notes and I press save, or when you swipe a credit card, you're actually saving information in magnets. So the black strip on the back of credit, the magnetic strip, the way it works is it is made up of hundreds of little magnets. And so hopefully you're familiar with what's called binary code, ones and zeros. That's how information is kind of stored and sent through computers. For magnets, you can store information via north and south poles. So imagine a credit card where it's made up of 1,000 magnets, where you have north poles facing up or south poles facing up. Well, if a north pole is facing up, that's going to correspond to 1 in binary code. And if a south pole is facing up, that's going to correspond to a 0. So when you swipe your credit card to a reader, the reader is simply just recording the magnetic field, whether it's a north or a south pole. From that, it gets a stream of ones and zeros, which is connected to your bank account or the credit card account, which then charges it. The same thing works for a computer. So inside of your hard drive contains literally billions and billions of little magnets. And when you press save, what you're doing is you pass electric current through your hard drive, and it rearranges those magnets, forming ones and zeros, kind of digitizing whatever information you're trying to store. That's why it's really important to not have magnets near phones or computers, because the presence of a really, really strong magnet can turn a north pole, flip it into a south pole, and now that 1 becomes a 0, and now this whole document could be corrupted from the fact that you moved some magnets around. Kind of interesting. Excellent. I'll have to save that for later. Any questions about that? No? Okay. So now we get to probably the big topic of the entire lecture, the reason why we're studying magnetism in the circuitry unit. And that is to answer the question, how are magnetic fields created? So it is a law of nature that magnetism is created by moving charges. So in other words, things like protons or electrons in motion, that's the key piece, in motion, are what create magnetic fields. If you remember the video we watched on Michael Faraday, he was the one that showed that moving electricity creates magnetism. So if we were in class, I would show you an electromagnet is a good example of this. So an electromagnet is just simply taking current and passing it through a wire. And when you do that, you can create a magnet. So if you ever look at like the trash yard, for example, they can pick up cars with these little tiny discs. It's because they're passing lots of current through to create a strong magnetic field. Now, just like how we had talked about how magnetic fields and electric fields are related, well, if moving charges like protons and electrons can create magnetic fields, there is a second law which says moving magnets can create electric fields or electricity. So that's the principle of how a motor works. So an electric motor works via passing electricity through a coil of wire and making a magnetic field. That magnetic field then interacts with another magnet and causes the motor to start spinning. It's the same principle of how electromagnetic braking works. So when we get to ride the ride of steel, when we go to Darien Lake, you'll see that the braking system works via a magnet passing through a chunk of metal. Or if you've ever ridden, it's called the motor coaster at Darien Lake. that propels you by passing current through a wire, which creates a magnetic field, which causes repulsion. So it's just electricity and magnetism interacting. Another fun example of magnets, the question, how do birds know how to fly south? So are birds little tiny physicists? Do they have like a sextant and a compass? Can they direct? What's interesting is, just like how you and I can see visible light, it's believed that birds are able to maybe see or understand magnetic fields. So it's not known whether or not they can actually see magnetic fields, but they can definitely feel magnetic fields, just like how you and I can feel wind or feel heat. And so we had talked about the magnetic field is strongest near the poles of a magnet. So for Earth has its two poles. So magnetic south pole is actually at the North Pole, and magnetic north pole is the South Pole. And the Earth has what's called a magnetosphere. So a giant magnetic field going out. That's actually, it's really important that the magnetosphere exists because there's charged particles being emitted from the sun all the time, and they get deflected by the magnetosphere. That we talked about in a second. But notice how these lines are really close together near the poles, and they're really spread apart near the equator. And so it's believed that birds know how to fly south because they're able to interpret where the lines are most dense and least dense, and so they're kind of following along those field lines. So an application, or kind of showing that the Earth has magnetosphere, is the Aurora Borealis, or Australis. Aurora Australis should be in the southern hemisphere. And so the reason we see these northern and southern lights, it has to do with Earth's magnetosphere. So the picture here shows the Earth and the Earth's magnetic field going around. This is a much better picture of what it looks like. And so we see, as the solar wind, which is a bunch of charged particles ejected from the sun, is sent forwards, well, we learned above that, you scroll to it, moving charges create magnetic fields. So every little charge that's moving, every little electron, for example, that's moving, has its own respective magnetic field that it creates. Well, that magnetic field interacts with Earth's magnetic field, which causes repulsion or attraction, depending on the spin and such. And so you see these charged particles that follow along the field lines to the poles. Now, later on in the year in this class, or you might have learned about in chemistry, you learn that when you excite charged particles to higher energy states, when they drop back down, they re-emit light. So the light that you're seeing, the Aurora Borealis or the Aurora Australis, is charged particles dropping down to a lower energy state and emitting light. And again, the energy came from the fact that because an electron creates a magnetic field, it gets pushed and pulled by Earth's magnetic field. So to summarize, anything that has charge, which is moving, creates a magnetic field, and therefore can be affected by a magnet. All right. This is a good place to stop. Any questions or things, any curiosities that you guys have at this point in time? Try to pause for at least a minute to make sure if anyone has questions. Okay, so continuing on. If we know that charged particles create magnetic fields, then that kind of gives us an idea of the origin of magnetism in the first place. So the origin of magnetism is electrons and spin. So remember, the most important statement that we're going to be talking about is moving charges create magnetic fields, and moving magnets can create electric current or electric fields. So if we were to look at something like a bar magnet, the reason why it's a bar magnet is it's made up of atoms or electrons that are all spinning. So I'm going to go ahead and open up my document here again to kind of show this. So we know if I have a magnet, for example, like a little bar magnet, we know that it creates this magnetic field, if I draw north, south, looks like this. But if we were to zoom in, we would see that this magnet is made up of little tiny chunks, which are called domains. They're kind of not uniform, like that. And so every little chunk of magnet is made up of electrons, atoms. And so in those electrons, you have spin. So electrons can either be spin up or spin down. And so in a material that is a permanent magnet, all of the electrons are spinning the same way. And so as a result, all the electrons spinning in the same way, you get a net resultant magnetic field that is created. Now, let's compare that with something like a pen. So this might be a bar magnet. Now let's consider what it might look like inside of this pen. Well, this pen is also made up of a bunch of atoms, so it has like domains as well. And so just, again, because it's made out of atoms which have electrons, these electrons are spinning. So then you might say, well, why is it, because this thing has electrons, why doesn't it create a magnetic field? Well, if we were to look at the electron spin in this pen, we would see that the spin is all disoriented. Every electron is spinning in a completely different way due to how the bonds that occur in it. And so the net result of all these little tiny magnetic fields is there is no net magnetic field lines that are created. This is like a piece of plastic. Now though, let's look at something called a temporary magnet. So, for example, a paperclip. Hopefully you've all done this before. You've taken a magnet and you've touched it to a paperclip and you notice that, hey, something which isn't magnetic on its own, I can magnetize in the presence of a magnet. So what that looks like is, if we were to look at a little tiny piece of paperclip, I'm just going to draw a paperclip like that. Normally, when it's just sitting there by itself, all of its domains are pointed in different directions, making it so the net magnetic field is zero. But in the presence of a magnet, for example, if I touch a magnet to it, a thing like a paperclip, its electrons in it are able to move around quite readily. When I do that, I'm able to rotate the atoms so they all line up. And so when I do that, it becomes a temporary magnet as all the atoms rotate into place and line up, creating a magnetic field. Then, as soon as I remove the magnet, or it depends on the material how long it takes, but in most cases, it's a few seconds after I remove the magnet, it returns back to its original configuration. Like that. So any object, if you have a strong enough magnet, you can actually magnetize any object. It just takes a really, really strong magnet to magnetize something like plastic, because it all relates down to the bonding, because these bonds, they're really kind of locked into their place, and they're really kind of tightly bound to being all not in order. But in something like this, they're much more loosely bound. As just like a little hint, there's a relationship between temporary magnets and metallic bonds. So things that are metals are more easily magnetized than things that are non-metals. So you can think about the bonds for there. Not hearing too many questions. Is there anything, does that picture make sense? It would help if I had the video up so I could actually see you guys. Are there any questions at this point?
So are they, like, you said that they spin, like, inside the material?
Okay, yes.
Material, or is that wrong?
So let me, that's a great question. So I kind of go back to this. So the origin of magnetic fields has to do with atoms. So recall that an atom has a nucleus, which is made up of protons and neutrons. And then around that nucleus are electrons, which are kind of moving around. And so...
Oh, so it is electrons.
Yeah, so what these electrons, in addition to charge and mass, possess another property. They possess what's called spin. It has to do with a thing called angular momentum. But basically, they can have what's called spin up or spin down. And so another piece is these electrons are moving around the atom all the time. So in like the Rutherford model, you think of it as them spinning around, which isn't exactly right. But at least it gives you the idea that, hey, these atoms are in motion. Or these electrons are in motion. So it is the result of these electrons moving that creates magnetic fields. Now, in a thing like a bar magnet, so a bar magnet is made up of billions and billions of little atoms. Okay, so I'm just kind of drawing the little dots to represent all the little atoms. And so in something that is a permanent magnet or possesses everyday magnetic properties, all of the electrons happening to be spinning in the same direction, so that all the individual magnetic fields created by the electrons all line up and form a strong magnetic field. So the difference between a strong magnet and a weak magnet is how well aligned these fields are. So for example, if I had a magnet where they're all perfectly lined up, this would be a very strong magnet. But
would it always
point
up, like, to, would it always point to, like, north?
Oh, yeah.
Like,
so,
you drew all the magnet arrows.
Yeah, so because of our rules, because magnetic fields go from north to south outside of a magnet, the way I've drawn it is correct inside a magnet. So if the bottom is a south pole, and if the upper part is a north pole, then they must be pointing up like that, yes, to create that field. So the idea is, one of the rules we're going to learn about magnetic fields, they have to curl around from north to south on the outside of a magnet. So then, as such, inside of the magnet, they have to go this way to kind of complete that loop. No, great.
So the electrons in the magnet are spinning the same direction?
Correct. That's the basic premise of it. Yeah, that in a material that is naturally magnetic, the electrons are all spinning in the same direction, or are mostly spinning in the same direction. Most of the time, for example, like, so we did the magnetic field lab with the bar magnets in school. Those are weak magnets. So for those, you might see like most of the lines are directed in the same direction, but then a couple are in different directions. So for example, like a picture like that might be what our bar magnets at school look like, where again, you see most of them, so you get a net magnetic field that looks like this, but it's not perfect. Did anyone in class see me remagnetize the magnet? And did anyone see what I did? Sorry, let me try if I can see. If you did see me remagnetize a magnet, could you unmute yourself and tell the class what I did? No one did?
Did you run electricity through it?
Yeah. So on my middle lab table on the side of the room, I have a device called a remagnetizer. And so you stick two magnets in, and then you connect a bar to the top, which makes a complete loop for current to pass through, and then you pass about 20 amps of current through it. That's exactly right. So by passing a tremendous amount of current through it, I can kind of realign those little domains temporarily. Because the bar magnets aren't really true permanent magnets, they're not great. But a true permanent magnet, they're a lot more locked in position. Okay, good. Let's hear some more questions, because those were great.
I have a question.
Yep.
So if that's what's going on inside of the magnet, how does that affect what goes on like outside of it, I guess? Like how does that make things stick to it? That makes sense.
Okay, good. So this is what's happening inside the magnet. So what's happening is all these little individual electrons are all adding up together to create essentially a magnetic field that goes like this and then curls around. So the presence of all those electrons creates the magnetic field that goes like that. So that's just one magnet. But in order for forces to happen, you need two magnetic fields. So then it is the interaction of two magnets which have their individual domains, which then result in magnetic forces. So I guess to kind of stepwise it, the individual electrons, when they're lined up, create a magnetic field, and then it is the interaction of two magnetic fields that results in a magnetic force. Okay. Any more questions?
You might have already answered this. I might have lost step. What makes a material to have like two poles? Like,
I'm sorry, could you speak up, Ludo?
What makes a material to have like the south pole and the north pole? Yep. So you might have already answered this. What makes a material, like in nature, to have a north pole and a south pole? Like,
okay.
What are they? How can
yeah, so to kind
I
of...
don't know, I'm a little bit lost on that one.
No, that's a good question, because I've kind of just stated that objects have north and south poles, and I haven't really stated where they come from. So I'm going to have to finish answering the question a little bit later in today's lecture, but the basic way to understand it is moving charges create magnetic fields, and so because you have spin up and spin down for electrons, when we have a north pole created, there has to be a south pole created. So the basic, I guess to answer your question is, because electrons spin and create magnetic fields, and because for every north pole there has to exist a south pole, if the arrow is kind of facing up, that creates a north pole, and then because there's an end to the arrow, that has to create a south pole. Does that answer it, or would you like me to try to answer it a different way?
No, and what creates the north
pole?
Like, and the origin, like, what is that?
What is the origin of a north pole? Is that your question?
Yeah, like how a material can have like these poles.
Okay.
What is that made of? Like, what is that?
Okay, so for that is actually a really, as far as I know, a difficult question to answer. So you're saying, how can an object have a north pole? What is the origin of it? So at this point in time, I can tell you that a fact or a law of nature is we observe that moving charges create magnetic fields, and we observe that for every north pole, there must exist a south pole. Those are actually, as far as we know, laws of nature, meaning you can't kind of go deeper down the rabbit hole. That's kind of where the statement ends. So to answer your question, there would have to be some other fundamental laws of nature which would explain it. So it's a really interesting question to ask, but I don't, as far as I know, think it can be answered.
Okay, thanks.
No, thank you. That was good. Okay, so because we now understand that it's the result of electrons and it's the result of moving charges that create magnetic fields, we can talk about how generators and motors work. So the first one is a motor. A motor uses electricity. Yep, question?
Can you scroll up? Because
Yeah.
Scroll up. Oh, for the picture?
Can you scroll up a bit so I can just read it? Yes.
Perfect. No
Yeah,
problem.
we went to you drawing stuff before we could write down that sentence.
Oh, of course. Yep, you got it. So yeah, the important part, moving charges create magnetic fields, moving magnets create electric current or fields. And so then the origin of magnetism, where it comes from electrons in an atom moving around. Asleep? Just give me a thumbs up when you're good. I think if you want to keep your video off, you can also do a thumbs up in the chat as well. I feel like, I can't remember, I'm trying to figure out where it is. But I know there's a button you can press that says like thumbs up, thumbs down. Oh, thank you, Ludo. Thank you, Sadie. Excellent. Oh, Katie, thumbs up. Thank you. Reactions button. So let's talk about then how motors and generators work. So the first one, a motor uses electricity to create a magnetic field to spin a magnet. So the very most basic motor you can have, let me go ahead and draw a picture of that. The most basic motor you can have looks like this. You have some kind of a large magnet, so like a north and a south pole, which creates a magnetic field. So imagine permanent magnets. Then you take a coil of wire like this, and you pass current through the wire. So what happens is, due to the interaction, because remember this current creates its own magnetic field, what you can do is you can visualize that current as loops. So it creates that little magnetic fields that loop around like that. So the idea is the purple lines I've drawn represent the magnetic field created from that current passing through the wire. So notice, if I have a permanent magnet and then I pass current through a wire, I create another magnetic field. This field and that field cause this loop to start spinning. And so that spinning is physically what an electric motor is. So, yes. Question?
We had a question from Zach in the chat. Yeah. He's wondering, does ferro mean iron, like a ferro cassette tape?
Thank you, Mr. L. So in chemistry, you probably learned about metallic bonds. So there is, so I'm trying to remember how to say this. So first, iron has the symbol Fe. So it's Latin for like ferrous. So there's two types of iron bonds. I think there's like iron 2 and iron 3. Because it's different, sort of valence electrons. I think if you hear iron 2, it's ferrous, F-E-R-R-O-U-S, and then iron 3, if I remember correct, is ferric. Like there's ferrous oxide and ferric oxide. So yes, ferro means iron. So in a cassette tape, Zach, it's the same idea as a hard drive or, I'm trying to think, a credit card strip. You're simply storing data on a cassette tape by rearranging the magnets or the magnetic strip on a cassette tape. So a cassette tape is nothing more than a magnet. I think you were the one, I think Zach, you even mentioned how you deleted a cassette tape by passing it through a magnet. Is that right? Possibly. Okay. Yeah. So it means iron. Yep.
Okay. So ferromagnets, are those like permanent magnets? Because you.
Yeah. So if you hear the word ferromagnet, it means iron magnet, and those tend to be permanent magnets. So if you pull out of the ground material called a lodestone, it's ferrous, and meaning it contains iron. And so lodestones are naturally magnetic materials. There's all kinds of different magnets you can buy. There's ferrous magnets, there's alnico magnets, aluminum, nickel, cobalt magnets. There's neodymium magnets, which are rare earth metals. Those are used a lot in wind turbines.
Okay, thank you.
It just depends on what they're made out of. Yeah, they're permanent. So the basic premise of all electric motors. So think about where you might see an electric motor. An electric car, a blender, anything that's spinning at all has a magnet, a coil of wire, and then when you pass electricity through that coil of wire, that coil in turn starts to spin, and then that kinetic energy is harnessed in some way or form to make your smoothie or to go forward in an electric car. It's kind of neat that it's such a simple principle that drives anything that spins that we utilize for technology. Questions about a motor? So, let me get rid of this. If you're familiar or heard of a term called a generator, something that generates electricity, it's just the exact opposite. A generator works by spinning a magnet to create an electric current. Because remember, we learned above, minimize this, that magnetism originates from moving current, and that moving magnets can create electric current. So they're kind of like two sides of a coin, if you will. So if we look at the Hoover Dam, which is a huge source of hydroelectricity, how the Hoover Dam works is you have all this water up here, which is really high up in the air. Therefore, it's at a state of high gravitational potential energy. And then as that water falls, gravity does work on it, which of course gives it kinetic energy. Ooh, that's a really powerful E. And so that water falls through it and hits what's called a turbine. I'm trying to write on here, it is not working well. And so the turbine, if you look at the picture on the right-hand side, the basic piece you need to see is there is the rotor and the stator. So the stator is, if I remember correctly, that is the magnet. So it's a big, no, I'm sorry. The stator is the coil of wire, and the rotor is the magnet. As the water flows through and hits the turbine blades, it causes the rotor to start spinning. And so a magnet begins to spin through a coil of wire. And remember, the statement was, moving magnets create electric current. By spinning a magnet through a wire, you're able to generate electric current. So in Niagara Falls, for example, all the electricity that's created from Niagara Falls is harnessing potential energy stored from water being high up in the air, and then turning that potential energy eventually into electric energy by just simply causing a magnet to spin through a wire. So, questions about that piece? Because with these two principles, if you understand how to harness electricity to move things and how to harness magnets to create electricity, that's how our modern world functions. If you think about everything that we have right now in this world, all of our electric appliances and all of our main forms of energy, they're all created and utilized in these two forms, motors and generators. Now you might say, well, what about something like coal, or what about nuclear energy? That's got to be different, right? It's actually not. So coal energy or fossil fuels, for example, work in a very similar way. They work by burning coal or burning oil to heat up water. That water creates steam, and just like how the water flow makes this turbine spin, by pressurizing that steam, they pass it through a turbine and make the blade spin to create the electricity, just like how the hydroelectric dam does. So coal and oil is just a really, really fancy way of boiling water to create steam to spin a turbine, to create electricity. Nuclear energy is even more fun. Nuclear energy is the most insanely complicated way ever thought of by humans to boil water. So you take radioactive elements like uranium or plutonium, and you have a very controlled reaction. And so that reaction gives off tremendous amounts of heat. So you stick a piece of uranium around water, and the heat that's given off from the radioactive decay heats up the water and creates steam, and then it's still the same process of turning a turbine blade. So if you think about all the electricity that we create in the United States, it all comes from this one piece, spinning a magnet around a coil of wire to generate electricity. More modern forms of electricity, like wind turbines, are the exact same way. Has anyone, maybe show like a thumbs or a nod, have you guys seen a wind turbine? Let's see, Hannah, Gabby, have you guys gone on a tour of wind turbine farms? Liz, have you guys seen them through New Vision?
No.
Oh, bummer, because I thought I remembered seeing that as one of your trips. So a wind turbine does the exact same thing as a water turbine, but instead of using water to spin a blade, a wind turbine just utilizes kinetic energy in the air. So the air makes the blade spin, and then inside of the rotor of a turbine is magnets and a coil of wire. And so it generates electricity just simply by harnessing kinetic energy out of the wind. The only one that's different is solar panels. Solar panels work via a different function, which we'll have to save for a different day. Okay. So what questions do we have right now? Because that was a lot of stuff.
So is the magnet like spinning in a coil, or is it spinning around the coil?
I'm trying to remember how it works.
Like, is the magnet outside spinning around it?
If I remember right, I think the usual, it could be either or, but I think the usual way is you have a coil of wire, and then you have a magnet on the inside, and I think usually it's the magnet that is spinning around the coil of wire. Oh, I'm cutting out? Is the voice not great? It's laggy? Okay, I guess I'll try to slow down. I guess I got a little too excited and I was talking a little too fast for Zoom. Sorry about that. What other questions do we have? Okay, so what this now leads us to, and this kind of goes back to Ludo's question, because Ludo was really alluding to the idea that just to remind you, she asked, what's the origin of a North Pole, or where do these things come from? And I had stated, I can't really answer that because these are kind of laws of nature. What I'm going to share with you are the laws of electricity and magnetism. And these are called Maxwell's equations. Now, be aware, these are written in a form of math that you haven't seen yet, so I'm not expecting you to copy down these equations or memorize them. I'm going to show you them, and then we're going to discuss them. So the statement is, all of electricity and magnetism and optics, which is light, which we're going to learn about later, can be summed up by 4 equations. So there's this little triangle here, that's a mathematical symbol, and then there's some dots and crosses. Those are mathematical symbols. But we see that there's 4 equations. Recall, E means electric field, B, I'm going to tell you, means magnetic field, and then this thing J means current density. You can think of it as current. So a really, what's called elegant or beautiful thing of nature is that everything in electricity and magnetism we've learned can be summed up from these 4 equations. So what I'm going to do is, I'm going to tell you these 4 laws of nature, and that'll kind of get into what Ludo was saying. These are the fundamentals. This is where everything kind of comes from. So this first equation, what this equation means mathematically is, electric fields diverge from charge. Or in other words, if I have a charged particle, electric fields go away from it. The second equation says that no magnetic monopoles can exist. Or in other words, the second equation says, for every North Pole, there must be a South Pole. So kind of getting at what I said earlier, it is a law of nature that for every North Pole, there must be a South Pole that goes with it, according to this second equation. The third of Maxwell's equations is called Faraday's Law. Notice we have an E and a B in there, and there's a little T term for time. So what this equation states is that a changing magnetic field creates an electric field. So changing magnetic fields create current and thereby create electric fields. So that's the statement how, if I have a magnet moving through a wire, I can create electric current. Finally, the fourth one, which is a combination of what's called Amperes Law and Maxwell's displacement current, says that current and changing electric fields create magnetic fields. And then also these magnetic fields have to curl or follow loops. So I'm going to break that down. First, the equation 4 says changing electric fields create magnetic fields. And it also says that magnetic fields have to loop. Or in other words, if I have a North Pole and a South Pole, they have to follow loops or curls around. Now, what's amazing about these 4 equations is, with those 4 statements, repeating again, electric fields diverge from charge, you can't have a north pole without a south pole. Changing electricity creates magnetism, and changing magnetism creates electricity. That actually will give rise to everything we've learned this unit, as well as everything we're going to learn in the upcoming units. 3 was,
3.
so Rowan asked, what was 3? Sorry, one more fast. 3 was what's called Faraday's law. A changing magnetic field will create current in electric fields. So that's the principle of an electric generator, for example. An electric generator makes use of Faraday's law because it spins a magnet, meaning it creates a changing magnetic field, and then that will induce an electric field or an electric current. Any other questions? That was a good one.
Could you go back to the equations, please?
Yeah, of course. So I'll try to, as I go back, I'll explain what these things all mean. So first off, the little p right there, it's actually, this row would know this one, it's the Greek letter rho. That means charge. So this equation you can see is charges create electric fields. And then this symbol here means the little triangle with a dot, meaning those charges, the electric fields have to diverge. So in other words, this equation says electric fields diverge from charge. The second equation says magnetic fields do not diverge. Or another, so rewording that, because magnetic fields don't go away, it means that you can't have a north pole without a south pole. The third equation, if we look at this term here, this term means a changing magnetic field. So this says a changing magnetic field creates a curling electric field. So in other words, if I have some kind of a magnetic field that's moving, it's going to create a changing electric field. And then finally this last one. This last one says current, that's the first term, and changing electric fields result in magnetic fields. So oftentimes, like physics is known for its jokesters and its memes. You'll see T-shirts or mugs, and there's a really popular one that says, "And God said," and then there's these 4 equations, and then there was light, because these 4 equations give rise to the theory of how light works, which we're going to learn about in our next unit, as well as all the properties of electromagnetic radiation. Good. What other questions do we have?